Hello and welcome to this lecture series on space science and technology from Indo Science Space Education Trust, Pune. I am grateful to the organizers of this lecture series for offering me an opportunity to talk to you on an interesting subject, improving lives, satellite applications. Friends, you know that of entire animal kingdom that dwells on this planet Earth. Humans are the only species that have striven to improve its life since its first appearance some 2 million years ago somewhere in Central Africa. Use of tools and devising new gadgets through acquired knowledge and experience to make his life more comfortable, wholesome and improvised is the hallmark of human beings. Exploring, understanding, knowing its surroundings, and then exploiting the resources that lay around is another characteristics of the Homo sapien. For a long time, the space remained an inaccessible frontier for mankind as we were shackled by gravitational pull of the earth. Invention of rockets that can pierce through the atmosphere and reach to the heavens enabled humans to exploit the frontiers of space. Practically, it all began on 4th of October 1957 when the then Soviet Union, the Union of Soviet Socialist Republic USSR, launched humanity's first artificial satellite, Sputnik, into space. The Sputnik was a game changer. It opened up vast and unimaginable vistas of applications of space for the betterment of humans on Earth. Today, myriads of applications of satellite in space has brought us to an era of pervasive technology. Pervasive technology means a technology whose importance is felt only in its absence. Think of our life without electricity, car, buses, airplanes, mobile phones, TV, radio, internet, global positioning systems, weather forecasting, disaster mitigation, cyclone warning, etc. etc. Satellite technology and its application is one such pervasive technology that has brought us an unprecedented improvements in our life. But what is a satellite? A satellite could be a moon, a planet, or a man-made machine that orbits a planet or a star or any celestial body. For example, Earth is a satellite because it orbits Sun. Likewise, the moon is a satellite because it orbits Earth. But usually the word satellite refers to a man-made machine that is launched into space and moves around Earth or some other celestial body in space. But we shall not restrict our definition of satellite as something that revolves around a body or a group of bodies. A satellite may or may not complete a revolution. Its path may be a section of an orbit round an object, but it still can be classified as a satellite. As you know, that in this vast cosmos, there is not a single object that moves independently without having any influence of another object or a group of objects. Earth and Moon are examples of natural satellites. Thousands of artificial or man-made satellites orbit Earth. There are satellites used mainly for communications, such as beaming TV signals, music, or even connecting two persons through phone calls around the world. Some take pictures of the planet that help meteorologists predict weather and track cyclones, and some use images taken by the satellites to predict crop yield, and still some to find natural resources, some take pictures of other planets, the sun, comets, or faraway galaxies. These pictures help scientists better understand the solar system and the universe. There are satellites that help you navigate anywhere on Earth and give your precise location on Earth and can even tell you at what speed you are cruising. Satellites come in myriads of shapes, size, and compositions, and hence are classified in many ways. This is because they are designed for carrying out specific tasks from a predefined orbit or a space path. Satellites can be classified by their distances from the Earth's surface, that is, their altitude, by their primary function, whether for communication or remote sensing or meteorology or for warning of natural calamities or simply as space probes for study and detecting cosmological phenomena out there in the universe. A satellite is always designed to carry out some specific tasks. For different tasks, different satellites are launched, and that's the precise reason why we have so many satellites in space. Satellites are also grouped for their size and weight: picosatellites, microsatellites, nanosatellites, and large satellites, etc. Why are satellites important? Actually, the bird's eye view that satellites afford enable them to see large areas of Earth in a single shot. A satellite at around 36,000 kilometers from Earth's surface can view one-third of the Earth's surface at a time. That is, a whole Earth disk facing it. This ability means satellite can communicate with one-third of the Earth and or collect more data more quickly and repeatedly than instruments deployed for the purpose on ground. Satellites also can see into space better than telescopes on Earth. That is because satellites fly above the clouds, dust, and particulate matters in the atmosphere that can block or at least degrade the view from ground level. To gain more insights and study the heavenly bodies like the moon, Mars, the sun, or other planets inside or outside our solar system, space probes are launched. Satellites can go very near to the targeted heavenly bodies and can make thorough studies of the body from a very close quarters. Some orbit the targeted heavenly bodies and some simply fly by. One thing should be remembered, that all objects in space, whether man-made or natural, orbit another object. Spacecrafts on flyby missions may not complete the orbit around a celestial body, but their path definitely is a section of an orbit. Hence, for the purpose of discussion, we shall categorize them all as satellites. But what is an orbit? An orbit is a regular, usually a repeating path that one object in a space takes around another body. An object in an orbit is called a satellite. A satellite can be natural like Earth or Moon. Many planets have moons that orbit them. A satellite can also be man-made like INSAT, GSAT, and IRS series of satellites of India. Chandrayaan, Mangalyaan, that you already know about them, and Voyagers are some other examples of satellites, though in space parlance they are called space probes. All orbits are elliptical, which means they are an ellipse, similar to an oval. Orbits have several parameters. We shall look at few of them. Satellites that orbit Earth, including the Moon, do not always stay at the same distance from the Earth because they are in an elliptical path. Satellites that orbit an object, say Earth, will always be at one or the other foci of the ellipse. The closest point a satellite comes to Earth is called its perigee. The farthest point is apogee. The period is the time a satellite takes to complete an orbit. For example, Earth has an orbital period of 1 year. The inclination is the angle of orbital plane that makes when compared with the Earth's equatorial plane. Nearer the orbit, shorter the period, and vice versa. For man-made satellites, there are essentially 3 or 4 types of orbits. Low Earth orbit or LEO, medium Earth orbit or MEO, and the geosynchronous Earth orbit or geostationary Earth orbit GEO. LEOs are from around 300 kilometers to about 500 kilometers above Earth's surface. Medium Earth orbit are from 400 kilometers to about 1000 kilometers. And geosynchronous are about 1000 kilometers to 36,000 kilometers. Satellites at 35,862 kilometers above Earth are both geosynchronous and geostationary. There are 2 special types of orbits: sun synchronous orbit or polar orbit, and the other one is Molniya orbit. The sun synchronous or polar orbit are preferred by remote sensing satellites. The reasons for this we shall dwell later. Communication satellites generally use geosynchronous or geostationary orbit. Most of the time they use geostationary orbit at about 36,000 kilometers above Earth. Molniya is a very special type of orbit. It's a very elongated elliptical orbit, and it's also in an inclined orbit. It is not on an elliptical plane. And this Molniya orbit is generally used by Russia and countries in the far north latitude. Now let's take a glance at different tasks. The specific tasks that satellites perform. Satellites have myriads of applications. Some of them are communication, remote sensing, meteorology, oceanography and ocean studies, telemedicine, infrared imaging, military reconnaissance, cartography, navigation, internet services, atmospheric studies, and of course space probes to study planets and the universe. Then there are satellites for search, detection and study of exoplanets. There are many other kinds of satellites. Well, it is not difficult to comprehend that each application is an ocean in itself, and each application commands few hours of detailed and separate presentation to give some justice to them. My friends, please understand that each image or video clip that is incorporated in this presentation commands separate and detailed presentation on each one of them. So naturally, we shall therefore discuss each one of them very briefly but crisply. That will definitely give you a taste of flavor of each one of them. Communications. Of all the activities that the humans are indulged in, communication and the expression of thoughts perhaps comes at the top of the list. Communication is not only between two humans or among humans, but also between devices and computers spread across all the corners of the globe. You know, before satellites, TV and radio signals didn't go very far. TV signals only travel in a straight line, so they would quickly tail off into space instead of following the Earth's curve. Sometimes mountains or tall buildings would block them. Phone calls to faraway places were also a problem. Setting up telephone lines over long distances or underwater is difficult and costly. Since radio waves travel in a straight line, they cannot travel far away as the Earth's curvature blocks them at horizon. To widen the horizon, the only way is to go up and up and up from the surface of the Earth, and that precisely is done by the communication satellites. Communication satellites. Since communications systems must provide round-the-clock services, the orbit chosen for communication satellite has to be geostationary or geosynchronous. In this orbit, the period matches exactly the period of Earth rotation, that is 24 hours. The altitude for this orbit is about 36,000 kilometers or 35,862 kilometers to be more precise from Earth's surface. Our Indian communication satellites, INSAT, GSAT, EduSat, etc., as well as communication satellites of most of the other countries, use this geostationary orbit. Satellites parked in this orbit are both geosynchronous and geostationary. From a reference point on Earth, the satellite seems stationary with respect to the Earth's rotation. This enables 24 hours uninterrupted communication. The video illustrates how a satellite parked in a geostationary orbit is locked to the Earth's rotation. 3 satellites to cover globe. Since each communication satellite at geostationary orbit covers 1/3 of the globe, theoretically only 3 satellites are needed to cover the entire globe of Earth. However, for more pressing reasons, this scheme of 3 satellites has never been put to use. With satellites, TV signals and phone calls are sent upwards to a satellite. Then almost instantly and after amplification, the satellites can send them back down to different locations on Earth. Salient features of satellite communications. Communication satellite enable interconnection of widely distributed network, provide broadcast services, that is one point to many points like TV and radio to the last mile. Satellite communication offers wide range of advantages. Few of them are listed here. As can be seen, satellite communication is a distant independent services. The biggest advantage it offers is broadcast capability to the entire globe. A cricket match played in England can be viewed throughout the world. Multiple access capability, wide coverage, wide bandwidth to accommodate hundreds of TV channels and simultaneous millions of phone calls, and caters to fixed as well as mobile services. India's constellation of communication satellites. India has deployed a constellation of communication satellites. Earlier they were named as INSAT, Indian National Satellite System. In their new avatar, they are called GSATs, geosynchronous satellites. Reaching to an inaccessible place. Since the satellites are distant, independent, and knows no boundary, it is possible to reach inaccessible places for communications. Disaster management. A satellite mobile transceiver enables one to send an SOS signal from anywhere on globe, and immediate rescue operations can be carried out. Voice, video and TV communications to far-flung areas. Voice, video and TV communications to far-flung areas are realized. Telemedicine. Since satellite enables point-to-point, point-to-multipoint, multipoint-to-point and multipoint-to-multipoint communications, it is possible that a patient in a remote far-flung area devoid of any expert medical doctor facility can upload his or her medical reports, electrocardiograms, X-ray investigations, etc. to an expert doctor and seek her advice. Dedicated communication satellites for telemedicine have been launched. Telemedicine through satellites have proved a boon to people of far-flung and difficult to access areas in India, and providing them quick consultation with experts and immediate attention can be given to the patient. Teleeducation. Dedicated communication satellites for teleeducation have been launched by India. With teleeducation, a countrywide classroom concept to any remote place or a village or even as small as Kasbah can be realized. Remote sensing. Let us now turn our attention to another function of satellites called remote sensing. One important application of satellite is remote sensing. It may seem counterintuitive, but a holistic or a bird's eye view of an object or an area reveals many things that a close quarter view doesn't. Remote sensing enables us to see, study, and extract important and valuable and quantifiable information in a single glance of a vast area, picture taken from a height. But what is remote sensing, by the way? A technical or a more accepted definition is to know or to estimate characteristics of an object from a distance and without even touching it. Basically, it is the science and technology of taking images of Earth or any celestial body or a portion of it from a distance using one or more of bands of electromagnetic spectrum. The electromagnetic spectrum. The electromagnetic spectrum, as you can see in this video, extends from radio waves to gamma rays. As you can see that the human eye is only sensitive to a very tiny portion of this entire EM spectrum. We call it the visual spectrum or the visual band. However, the sensors that is cameras mounted on satellites can be designed to take images of objects in bands other than the visible also. That is possible with the human designed sensors, not by human eye. To take pictures, the cameras of remote sensing satellites either use sun's radiation that are reflected or scattered from the surface of the object of interest, or use the thermal radiation that are emitted by the object due to its thermal state. This type of remote sensing is called passive remote sensing, as it depends on sun's radiation for image capture. India's remote sensing satellites like Resources, Cartosats and Landsat series of USA are typical examples of passive remote sensor. Microwave remote sensors, however, use microwave band of electromagnetic spectrum. Microwave remote sensors emit microwave radiation from the satellites to illuminate the object of interest. Just like we use torch in the night to illuminate the surroundings to see. The microwave reflected radiation is captured by the sensitive microwave receivers on board satellite to construct an image. This technique is called active remote sensing, which affords us to see in the night and also through the clouds. Radio imaging satellites or RISAT of India is a typical example of microwave remote sensing satellites. The microwave remote sensing satellites or active remote sensors are also used for strategic applications. Polar or sun synchronous orbit. Remote sensing satellites typically use polar orbits instead of orbits on equatorial plane. The sensor has only one-dimensional array of photodetectors taking image of a very thin strip of Earth's surface below in the X direction. However, you know that a picture is a two-dimensional entity, X and Y. But as shown in the video, the satellite's motion from pole to pole can create a strip of images to scan the Earth in the Y direction. That is the other missing dimension of the image. Now, as the Earth rotates from west to east around its own axis, the satellite in its next orbit will scan another strip of image. This way, after a fixed number of orbits, the satellite would have scanned the entire surface of the Earth as shown in this video. Depending on the altitude of the satellite, after a fixed number of orbits, the satellite views the same spot on the Earth again. This successive viewing period is called the revisit time, or in remote sensing paradigms, temporal resolution of the sensor. Indian electro-optical sensors. Here in this image you can see an array of cameras or sensors that have been flown to space. These are all Indian built and designed remote sensors. Please note that these are not remote sensing satellites, but these are only cameras or sensors that are mounted on a satellite body so that the satellites can perform remote sensing functions. These cameras can take pictures in visible and near infrared portions of the EM radiation. They have different spatial resolutions, starting from 1 kilometer of Bhaskara satellite to sub-meter resolutions of Cartosat. Let us see some of the images sent by these cameras. This is an image captured by IRS-1D satellites of India. Image is of a large agricultural land. Notice that the image has different colors in addition to green. It is called a false color composite or FCC in short. This is done deliberately to segregate different crops and features on the ground from one another. You can see that in the given area, banana, corn, tobacco, chili, pulses, etc. are grown. It is possible to not only estimate the crop yield much in advance, but also the information about the diseases that could have afflicted the crop. Apple orchard. This image shows apple orchard in Shimla. This too is a false color composite. Forest cover. Here in this image you can see 3 images taken over a period of 2003, 2005 and 2006 year of a place in India. This temporal images clearly show the growth of vegetation taking place at the site. Underground water. Remote sensing techniques can be used effectively to detect underground water resources. With Indian remote sensing satellites, the strike rate to find the rate is as high as 95%. Soil moisture. In a similar fashion, soil moisture of agricultural land can be checked regularly. Drought condition. Crop yield prediction using satellite imageries also open up possibilities of drought prediction as shown in this image of state of Karnataka. Oil spills. Since the reflection characteristics of sea, water and mineral oil are different, it is possible to detect oil spills on sea. Urban planning. High resolution meter and submeter imageries from space open up tremendous possibilities for rural and urban town planning and rural management. With submeter resolution, you can see that even a small feature like cars or trees can easily be identified. This better helps in urban town planning. Summing up of applications of RS. To sum up, the remote sensing techniques are useful for agriculture and crop yield, marine and biological wealth, water resources and geology, ocean sciences and ocean studies, environmental ecology, rural development and urban planning, cartography, that is the map making science, weather modeling and global change, etc. Weather study and forecasting. 24 hours of uninterrupted viewing of any country or continent by a satellite parked at a geostationary orbit enables meteorological studies for weather forecasting. Coupled with infrared imaging capabilities, truly day-night monitoring of cloud cover, weather, cyclone, fires, or other natural phenomenon can be detected. Many of India's INSAT, GSAT and Kalpana series of satellites are placed with precision spatial meteorological instruments called VHRR. Since a satellite put in a geostationary orbit always looks to the one-third of the Earth disk facing it, it can be effectively used to monitor weather, study weather, and make forecasts of change of weather. India has launched dedicated meteorological satellites to address these functions. Satellite navigation. Let us now turn our discussion to some other applications of satellite. I am sure everyone who is watching this presentation must have used or at least seen someone using a mobile GPS or global positioning system app at one time or the other. Reaching an unknown place has always been a difficult proposition in the days bygone, but not anymore now, thanks to mobile navigation services with satellites. With GPS and other similar such services, it is possible to find the way in ocean where you may be surrounded by water and no land in sight, or in a desert where you don't find any landmark, or even in a metro city full of maze of similar looking streets and lanes. Satellite-based navigation systems have proved an unprecedented boon to the entire humanity. We use them so frequently that we wonder how we used to find our way when there were no such systems. Global and regional positioning systems. USA was the first to put this system in operation, which can give you latitude, longitude and altitude of any point on the earth. It is called the Global Positioning System, or simply the GPS. Google has designed a special application, both mobile and computer. We all know Google Map. Using this GPS facility that eases navigation for you. USA's GPS or other such systems offer two types of services: standard service and restricted service. Standard service is available to all free of cost, whereas the restricted service is available only for strategic use by the military. Many nations have launched such satellite navigation systems and services. Few of major ones, let us see them. The GPS is the Global Positioning System of USA. IRNSS, or Indian Regional Navigation Satellite System of India. It is also called Navic, an acronym for navigation using Indian Constellation. This is not a global system but only a regional system. Beidou, this is China's global satellite navigation system. GLONASS, a global navigation system of Russia. Galileo, a global positioning system of Europe. GPS of Europe. Trilateration. Satellite navigation systems use a technique called trilateration. If a place on Earth, say X, whose exact location is not known, but its aerial distances from three other points on Earth are known precisely, then it means that the unknown place is located anywhere on the periphery of three circles whose radius is the distance from unknown place to the known place. This means that the location of this unknown place X ought to be at the intersection of three circles as shown in this video. Trilateration, 3 dimensions using spheres. However, in reality, instead of circles of known radius, imaginary spheres are used by satellite navigation systems, as it can find location of an unknown place in X, Y and Z directions. The video being played here shows how this is done on a 3-dimensional space with 3 imaginary spheres constructed in space. In this, a point on Earth is viewed by 4 or more than 4 satellites. Each satellite emits timing signals which are received after a finite propagation delay by the receiver, that is your mobile in this case. This delay varies as per the distance of the satellite from the receiver. Since the velocity of the timing signal is known, which is the velocity of light, and the delay time is known precisely, it is easy to compute the distance of each radio visible satellite from the receiver. Additionally, the satellite's exact position in space is also known. Viewed the other way, it means the location of the receiver is anywhere on the surface of an imaginary sphere, whose radius is the distance between the satellite and the receiver. This distance is known precisely. Now 3 such spheres formed by 3 different satellites will intersect each other only at one point, and that point is the receiver location X. Hence, only 3 satellites distances are required to compute the exact position of the receiver using this trilateration method. A 3-dimensional sphere representation is shown here, where A, B and C are 3 satellites whose imaginary spheres intersect only at one point, and that is the location of the point of interest. The GPS of USA. The Global Positioning System, or the GPS of USA, uses 24 satellites parked at an approximately 20,000 km orbit above Earth. As shown in this video, any point on Earth has a radio visibility of at least 4 satellites at a time. Usually, more than 4 satellites will be visible to the receiver. As said, minimum number of 3 satellites visibility is enough and required to compute the location of an unknown place. 4th and additional satellites are used for precision and confirmation of the Indian Regional Navigation Satellite System IRNSS is our own indigenous navigation system. As opposed to the global navigation systems, this one is a regional navigation system. That is, it caters to navigation requirements of India and the region of approximately 1500 kilometers boundary outside Indian boundary. IRNSS is rechristened as Navic, that is navigation through Indian constellation. Navic architecture. Since it is a regional navigation system, we do not require so many satellites orbiting around the globe. Instead, only 7 satellites parked at geostationary orbit is sufficient. Navic features. Navic offers a host of features like terrestrial, aerial and marine navigation, disaster management, vehicle tracking and fleet management, integration with mobile phones, precise timing, mapping and geodetic data captures, and terrestrial navigation aid for hikers and travelers, visual and voice navigation for drivers. Now, let's turn our attention to another application, a very important application of satellite, that is the World Wide Web or the Internet services. You know, friends, that Internet has proved a real game changer. Started by DARPA of USA for its internal use, today it has engulfed the entire globe. As humanity cannot live without oxygen, it can also not live without Internet or the World Wide Web, WWW. Internet services use combination of satellites, terrestrial fiber optic or copper cables and submarine fiber optic cables for its operation. But the last mile connection, that is the connection to your home, is always a physical cable, be it a copper or an optical fiber. The Starlink. However, Elon Musk of SpaceX company USA is up to change the rules of the game. He has come out with a project in which he is offering a satellite-based internet services. This service is similar to DTH or direct to home TV channels. He intends to provide internet connections to all through satellites. Starlink operation. Starlink is a satellite internet constellation operated by SpaceX of USA, providing satellite internet accesses to most of the earth. Presently, the constellation consists of over 2000 satellites and will eventually consist of around 5000 or even more of mass-produced small satellites in a very low Earth orbit, that is VLEO. These satellites will communicate with designated ground transceivers. While technical possibility of satellites internet services covers most of the global population, actually the service can be delivered only in countries that have licensed SpaceX to provide service within any specific national jurisdiction. As of November 2021, The beta version service offering is available in 21 countries. The company intended to utilize the very little used V band spectrum of the electromagnetic spectrum for communication and internet operation. They intend to use a new orbital regime, that is very low Earth orbit regime of approximately 340 kilometers altitude. At this low orbit, the atmospheric drag is quite high, which normally results in short orbital lifespans for the satellites. That is, the satellite will not have a very long lifespan. This very low Earth orbit VLEO is required for instant communication, as in internet phone calls, video calls, online TV, etc. etc. The latency or the time latency ought to be minimum as possible. This can be achieved only if the satellites are practically as near to the Earth as possible. Since the lifespan of the satellite are short, the SpaceX needs to replenish the dead satellites frequently. These satellites are equipped with intercommunication, that is, they will not only support internet services but are capable of talking and interconnecting to each other, thereby enabling them to perform communication chain such that a shortest path is established between the users. Experimental data shows that the time latency from New York to London is only about 50 milliseconds, which is quite good. However, astronomers have raised concerns about the constellation's effort or constellation's effect on ground-based astronomy, as satellites' brightness due to reflection from the sun can interfere in their observations. Moreover, the satellites would add to an already jammed orbital environment. SpaceX has attempted to mitigate these concerns by implementing several upgrades to Starlink satellites aimed at reducing their brightness during operation. The satellites are equipped with krypton-fueled Hall thrusters, which allow them to deorbit at the end of their life. Additionally, the satellites are designed to autonomously avoid collisions based on uplink tracking data. Space probes. Satellites have tremendously enhanced our knowledge of not only our planet Earth, but also of other celestial bodies. We have gained insight on our neighboring and far-flung siblings of our solar system through the use of satellites. Some of the spacecrafts, or more appropriately, the space telescopes, have opened the doors to the deepest regime of the cosmos and even endeavoring to find an Earth-like habitable worlds beyond our solar system. Probably in future, their findings may provide an answer to the perennial question, are we alone in this universe? But first, let us take a look at our Earth's neighbors, the Moon and Chandrayaan-1. As you know, my friends, that Moon is our nearest neighbor. India has sent two probes to the Moon, Chandrayaan-1 and Chandrayaan-2. Both the probes, Chandrayaan-1 was only an orbiter and Chandrayaan-2 was an orbiter plus lander. But as you know, the lander could not achieve its function. Both the orbiters, however, have thoroughly studied the composition and terrain of the Moon. Chandrayaan-1 was the first to find and confirm the existence of water on Moon. Of course, before Chandrayaan-1, there were about 86 missions flown to Moon by other spacefaring nations. The Lalande crater. This image shows the mineral composition that was detected by hyperspectral imager or HI-C of Chandrayaan-1, Mars, where life might have evolved in the past. Of all the siblings of our planet, Earth, perhaps the Mars is the most studied sibling. This is because it has many semblances with Earth, and there are strong indications that probably life might have evolved there somewhere in the distant past. Mangalyaan 1. India launched a space probe to Mars, the Mars Orbiter Mission, or MOM. Of course, MOM was more popularly known as Mangalyaan 1 in November 2013. Of course, we were not the first to reach Mars, but nonetheless, it was a debut success. That is, in our very first attempt, we achieved a success reaching Mars. Perhaps of all spacefaring nations, NASA has exhaustively studied Mars. Images of Mangalyaan 1. Here you can see some of the stunning images of Mars captured by Mars Color Camera or MCC on board Mangalyaan 1. Mangalyaan has revealed many unknown features of Mars. The Hubble Space Telescope. In the year 1990, NASA of USA launched Hubble Space Telescope HST, and it is still functioning. HST has been an unprecedented success. Hubble's discovery. The Hubble Space Telescope HST has made a number of stunning discoveries. In fact, the humanity has gained thousands times more knowledge about our universe and about our other planets through the use of Hubble Space Telescope than what we have gained in the last 400 years since Galileo trained his telescope towards Jupiter. Hubble Space Telescope has discovered hundreds of galaxies, nebulas, dust clouds, and breathtaking phenomena never before seen even through the most powerful telescopes on Earth. In fact, Hubble once trained its telescope to a very dark region of the universe where there were no stars and no galaxies. But to the surprise of the scientist, Hubble found thousands of galaxies there. Quest for other worlds. Are we alone in this universe? Till today, we haven't received a confirmed answer to this perennial question. To find out whether life exists elsewhere or there are habitable worlds out there beyond our solar system, NASA has launched two spacecrafts, Kepler and James Webb Space Telescope or JWST, to attempt to answer these questions. The Kepler Space Telescope. Kepler Space Telescope essentially detects extrasolar system planets or exoplanets. It does this through a method called transit method or occultation graph or transit method for detection of exoplanets. When an exoplanet passes in front of its parent star, as shown in this video, it obscures the starlight depending on the size of the exoplanet. This obscuration in light, that is the fall in the light's intensity, is detected by the very sensitive detectors on board the Kepler telescope. It is also possible to compute the size of the exoplanet and how far it is from its parent star from the time it takes to transit from one end to the other end of the star's illuminated disk. Armed with two parameters, size and distance, it is also possible to compute the mass of the planet or the exoplanet. This way it is possible to know whether the exoplanet is in the star's habitable zone or not, just like our Earth is in the habitable zone of Sun. However, to know atmospheric composition and availability of water or other elements on the exoplanet and in the atmosphere, a more deeper study is required. James Webb Space Telescope offers this possibility. There may not be any viewer of this presentation who would not have heard about the James Webb Space Telescope, or JWST in short. You know, my friends, very recently in January 2022, last month, NASA launched humanity's most ambitious space telescope, that is JWST. JWST, which has a 6.5 meter diameter primary mirror, can peep into the distant past of up to 18.4 billion light years depth of our universe. You know, the scientists have computed that the Big Bang occurred somewhere around 18.8 billion years ago. When operational, the JWST perhaps will solve many riddles of the universe. Among the other tasks assigned to this telescope, one is to study in detail the composition of the atmospheres of exoplanet. Let's see how it does this. The near-infrared spectrograph. The scheme shown in this image shows how the JWST will study the composition of atmosphere of an exoplanet. This image, however, is an extremely simplified plan of the near-infrared spectrometer on board the James Webb Space Telescope. You know that the starlight consists of the entire spectrum of electromagnetic radiation. When this EM radiation passes through the atmosphere of an exoplanet, that is, when the exoplanet is transiting from in front of its parent star, the parent star light passes through its atmosphere. Now at this time, the spectra of the exoplanet undergoes some changes depending on the elements present in the atmosphere. The elements present in the atmosphere absorbs a particular wavelength of EM radiation depending on which element is present. The quantum of absorption depends on the quantum of presence in the element. This will be seen as a black line or a dark line on the spectrograph as shown in the image. The two black lines shows presence of sodium in the atmosphere of exoplanet. This exoplanet is called hot Jupiter, or by its technical name HD 209458. Friends, there is no end to these applications of satellites and how they have influenced and improvised our lives. But one has to put a full stop somewhere. My dear friends, before I put a full stop, I would like to tell you that these tons of knowledge and unprecedented improvement in our life that we have acquired, and the knowledge that we have acquired about our surroundings and the universe is all by sitting over here on Earth. If we imagine the cosmos as an infinitely vast ocean, then Earth is definitely a tiny shore of this ocean. The American astronomer Carl Sagan has rightly said that the surface of the Earth is the shore of the cosmic ocean. Sitting on the shore, we have learned most of we know. But recently we have waded a little out into the sea, enough to dampen our toes or at most wet our ankles. The water seems inviting. The ocean calls. Thank you all, my dear. Thank you very much.